time. Our stream is still experiencing issues. Okay. Stream quality is good. Not terrible. Okay. That was weird. It had to happen eventually. All right, are we all still here? Cool. Most everybody's here anyway. All right, how's this working out for everybody? Okay. Awesome. Sorry, I was looking at my stream settings and I was getting like 75% dropped frames. He's back. Woo! Most exciting class you'll ever take on Twitch. Oh, yes. And if the professor doesn't come back within 5 minutes, you can leave, right? Isn't that how it works? Alrighty. Well, that was our hey, how's everything going time. Hope you all had a good Thanksgiving break. I know I did. And yeah, we have 2 weeks of class left. So we have this week, and then we have next week, and then Monday is your final exam. And if we remember back to day one, final exam is a project presentation, right? So please all try to be there. You have your lab due on Friday, so don't forget about that. If you, why is your max quality settings? Could be that I'm dropping, let's see. I don't know. Sorry. It's normally not that bad, right? I'll have to look at Streamlabs later on and see what's going on with my quality. I'm guessing it's capping it. Normally it's not that bad. Usually it's like 720. Yes, so it'll be like the midterm. We'll do a Blackboard or a Zoom session on our exam time. I'll give you all, it'll be very similar to your midterm presentations. I'll have I'm actually going to be putting out the rubric probably in the next day or two for all your final documentation and your presentation, all that fun stuff, so that you can prepare for that. Basically, your last homework assignment, which I've got at the end of these slides, is going to be your final documentation. So requirements, some test cases, um, clean everything up, link everything together, basically. Sounds like a lot. It's basically just some paperwork. There's not a whole lot of mental hurdles to get over for this one. Um, Depending on your preference, you can record them as well, but it'll be again, a collaborator, a Zoom session. So whatever you're more comfortable with. And what else? Oh yeah, so other thing too, because we're coming up on the end of the semester, what I normally like to do in class is to dedicate 1 or 2 classes to group work, basically. So I'm thinking that this Friday and possibly next week Friday, we will be doing, I might give Zoom another shot. I heard they made a bunch of updates, but I'll probably have you all work in breakout rooms in your groups, and I'll kind of pop in from room to room and see how everybody's doing. Basically, I just want to give you some in-class time to work together and to make sure that everything's still going okay. I'll send out an announcement for that as well, but yeah, we're coming up on the end here. So hopefully everything is working out for you all for this class. Oh yeah, that's what I was trying to announce before the stream died. So if you were having issues with the lab that we did on the last week Monday, and if you're using IntelliJ, check that follow-up announcement that I sent out. Basically, it is instructions for hooking IntelliJ up to Travis. Uses Gradle instead of Ant. I know I've seen Maven guides out there as well, but Gradle was it was easier than setting up Ant, honestly. So if you're doing the IntelliJ route, give that link a shot, or the write-up a shot. I had zero issues the first try. And again, I'm not a Java person, so if I can get it, I'm sure all of you can as well. But other than that, let's crack on here. If I could get somebody to pop in chat when it's 10:40, I want to talk about your next homework because I know there's probably some questions about that as well. So I'll skip to the end if we're at that point. But the rest of our talks are going to be about verification and validation. So we started getting into unit testing, right? And I gave you kind of a big info dump on some of the other testing methods that are out there. We're going to look at a few of them in particular. I'm going to give you some more unit testing definitions today and a little bit more on integration testing. We're also going to start talking about coverage. We'll start talking about basically formalisms, so some of the verification activities. You're looking at logic and path branching and all kinds of fun stuff like that. Might even look at one of the formal modeling tools if we have time. But yeah, there's basically two aspects to quality assurance in software. There's verification and validation. Validation tends to be more in the testing realm that you've seen so far, like unit testing, integration testing, basically making sure things work the way you say they are. Verification is the flip side of that, and that's going to be making sure that you are building things correctly. So there's a lot more formal rigor with verification. And to give you, actually, before we get into that, today's going to be more in testing. Next time will be more in verification. I personally am more of a validation person. So I like testing. I like test cases. I like demonstrating that things are doing what they should be doing using the real world. Verification tends to be more in the real world, it tends to be more like code walkthroughs and checking things. If you get into the more research areas, more advanced software, there's like model checking. There are mathematical proofs that you can write out to make sure your code is performing correctly. But that is just demonstrating that they perform correctly in this contrived simulated scenario, not the real world. But the real world's harder to test everything. You get that with the formalisms, but we'll get to that. Just wanted to contextualize some things. I thought it'd be fun to start out class with some lovely quotes. This isn't in the PDF in Blackboard, so next time I'm in there, I'll have to update it. But I thought it'd be fun to check out some testing quotes and slow fade in with pretty cursive text. All code is guilty until proven innocent. I like this one. Fast, good, cheap. Pick any two. That's your basically a nice little translation of that agile triangle, right? If you want it fast and good, you can't get it cheap. If you want it cheap and fast, it's not going to be good. Kind of a real quote that you might have to experience at some point. Quality is never an accident. It is always the result of intelligent effort. Verification and validation, regardless of whichever path you're going down, it's going to take some effort to make it work right. Basically, it's not something to just slough off until the end. Last but not least, it's more about good enough than right or wrong, or than it is about right or wrong. So with testing and with any of these quality activities, and when I say quality, that's more like quality assurance or software quality. Basically, you're never going to test every single possible use case. It's just mathematically impossible. You are never going to cover every situation, but you can get good enough. And if it is good enough, then it's generally releasable. All code is guilty. Guilty of what? Guilty of everything. Basically, your code is always kind of suspect. Or sorry, it's always kind of sus. Yeah, use the Among Us lingo there. All right. I like these quotes. These honestly feel like things that real people would say. But yeah, that's kind of the thing though. Good enough is a hard pill to swallow because you want your code to be perfectly tested and you want it to always be accurate and correct and perfect, but it will never be that way. There's always going to be some situation that comes up that you never anticipated. Whether it's Hello World, whether it's an autonomous vehicle, there's going to be something. The key is going to be providing strategies to handle those situations when they come up. Provide a fail-safe state, provide a black hole safe kind of a configuration that your system can kind of go through if you're experiencing an error. Your try-catch blocks are the simplest example of that. Defensive programming. All right, so verification and validation. I mentioned there is kind of a schism here, a split between the two. Verification is making sure that the software conforms to its specs. Are we building it right? Validation's the other side. These are the activities that make sure the software meets the customer's needs, the customer's expectations. Does it do the thing in the real world? Whereas verification is, are we building the thing to these specs? So it's kind of a weird dichotomy here. We've seen this quote a million times already, right? Are we building the thing right? Or are we building the right thing? Basically, more theoretical, kind of mental driven would be my take on verification. Validation is checking to make sure it does that with testing effectively. There's a much deeper definitions than I've given you here. Probably some of the academics would get mad at me for simplifying it that way, but that's how it's kind of taken. All right, so V and V. What we are doing is we are basically promoting trust in our systems. If you don't test, if you don't verify, nobody's going to trust that your code does what it should, right? Simple program or a very complicated autonomous system, make sure you're checking it over. Now, question. If we perform a rigorous verification and validation strategy, and maybe you're doing test-driven development to build up those test cases as you go, you do a million code walkthroughs and you model out your system, check all the states. Is it free of defects, right? Have we tested everything? Is there going to be a fault that we experience? It's impossible to tell, is kind of the takeaway here. Now, it's good enough for its intended use. Again, that good enough quote there, we meet our test cases that we have derived. And that's going to be driven by what your customer tells you they want, maybe what the clients are expecting, what your internal quality process is. At its core, you're basically checking to make sure, is every requirement that you've written out, is there enough test cases attached to every single requirement that you can safely guarantee that your software will work as anticipated? Right? If you're modeling out an autonomous vehicle, you'd better have a whole bunch of test cases for every requirement to see, well, what happens if we are out of bounds for what values are coming in? Is the program just going to choke and die, or is it going to maybe try and do something intelligent there? Are we going to throw away the value and go with our default state? What if the user taps this button 50 times because they're impatient? Are you going to submit their credit card information 50 times? They're going to click it once and disable the button so that we protect the user from their own stupidity. Again, you're never going to anticipate everything, but it's going to be good enough. And good enough is going to be, is your software doing what you're saying it's doing and what the customer is expecting it to be doing? So kind of what I want to get into you today is verification and validation. Have we done enough to release it, basically? And if you haven't done enough, that gets into that ethical quandary. So let's talk about verification. We have, if we're looking at the verification side of things, we have dynamic and static verification. So you can think of dynamic as a form of testing. Now, it kind of, again, kind of depends on your perspective on where you're including testing. I put it more in the pure validation state, but there are those that argue verification and testing go hand in hand. Basically, you have this system which you are going through various testing states, test cases, making sure that your functions are returning the correct data or that it's expressing the correct behaviors. You are applying this test case to some version of your code. And I realize in here, for some reason, that I have some weird spacing going on here. And if we remember back to last time we talked about test cases, you're going to have some input values, you're going to have a set of steps to perform. Then you're going to have some expected output values and the actual output values. The dynamic side is, does your system do what you're expecting it to do? Does the actual test match the expected test? If you're looking for a further definition, that's actually called the oracle. Basically, it's telling you, does your test case pass or fail? Does actual meet expected? Pass. Does actual not meet expected? Fail. So things are happening live. That's why it's dynamic. The static side would be your static code analysis types of tools. Any of you ever play around with the lint at all? Let's see how my stream settings are back to being good. That's good. So basically the static analysis, and there's many tools out there, lint is one of them. Basically, are your variable types matching what you're expected to have? Are you following a particular coding standard? Does your code actually implement the requirements correctly? Basically, there is a lot of different kind of subsets of static and dynamic verification. The simplest static analysis tool is just checking data types, checking, um, again, coding standards. Like if you have a if statement, you must have an else statement. Otherwise, you violate the standard, for instance. Now, not just that, you can also handle um, code walkthroughs. So doing like a presentation of this module you've developed to your team and walking through it line by line and saying this is my logic behind this and this and this. This is how I'm implementing this code. Then you get that feedback on the actual function, for instance, or the class. So it doesn't have to be an automated tool. It can actually be a meeting in the real world, or probably Zoom these days. But here'd be a one kind of example of some kind of a static analysis process here. And this looks very complicated, and it can be very complicated. It can be very simple, just depends on what you're doing. But effectively, what you're doing in a static analysis is taking your source code and turning it into different representations to try and figure out, are there any simple problems that you've overlooked? So for instance, in this, again, very somewhat complicated process here, let's take our source code. Let's figure out, okay, what are all the variables in here? What are all the data types in here? Let's extract a model, and a model being like a visual representation, maybe a hierarchical tree of how all these variables interact with each other. So if you create an ID variable, maybe that is directly connected to a person class, which is connected to a course in university or something like that. Just kind of extrapolating here. You can also create an abstract syntax tree or a control flow graph. So I've got this guy here and this guy here. If any of you have ever played around with like compilers or with interpreters or anything like that, basically you're taking high-level programming code and turning it into a data structure that the computer can understand. And what do you get when you do that? Well, you have a software artifact that can be parsed out with, say, automated model checkers. Or you can check to see, hey, do we have any code blocks that are in this tree that shouldn't be there? Or if you look at this control flow graph, this is basically showing how a program goes from step to step to step. It's kind of hard to see, but here we have a loop. Here we might have a loop kind of a thing. Do we have any forever loops that need to be fixed? Do we have any dead code branches where it just kind of goes nowhere and stops? So there's basically all these different representations which static analysis is turned into kind of internally. This happens behind the scenes in a tool like lint or when you compile a program. Generally, you would compile, you run, you get your executable or your Java jar file, life is good. You don't care about what's happening behind the scenes, but really you're turning your program into concepts like this and then doing stuff to them. In the static analysis aspects, really gives you like extra power to check your code. If it's automated in this particular representation here, It's going to tell you, hey, dummy, your data type is wrong. You have a loop that never exits. You know, this branch leads you to an early termination state. Are you anticipating this? You're not following your coding standards, meaning that when an auditor comes in, they're going to have a massive heart attack when they look at your code base. So all these little things, they kind of build up over time. And again, it doesn't have to be automated. It can be a walkthrough. It can be a meeting to make sure that we have followed all of our guidelines, and then we can check off this step and move on to maybe an integration phase. So question for you all then. If we take the definition of verification and validation, um, actually, I thought I had a slide here, but I don't. So if we take the idea of verification as that we are building something to our spec and validation as the customer is happy with the output, again, kind of a simple definition, can we use them together? It would be a question to you all, assuming the stream has caught up here. Just love having my nice, well, they're not noise canceling headphones, but I can kind of hear kids just screaming in the background because they're unhappy with something. Doesn't throw off flow at all. All right, so here's a point. Verification and validation can be used together. Right? If we take verification as a model checking procedure, if we take it as formalizing, that our code is doing what we say it should be doing. Validation is the other side where we're checking it in the real world. These can absolutely be used interchangeably. Not interchangeably, but they can be used together. So let's say that I'm doing a model checking activity. And I know I haven't really defined model checking, but let's say that we have a control flow graph of our program. Right? So int main, we go into the function, we have an if statement, it branches, one of them goes into a loop, the other one continues on, they meet up at the end, and we return whatever we wanted to do, right? Control flow graph. We could run a model checker on here to say, does every branch get executed at least once? Do we have any dead code branches, for instance? Is there ever a case where this node is misconfigured? Maybe we can generate some input conditions that break this model, right? We have a suddenly unanticipated line of code going off into the ether because whatever conditions we gave it. A model checking activity would check that and test for that. This will be in some simulated environment though, right? It'll be within the realm of this model checking program. If you've ever heard of like Prolog or Spin or Alloy, any of these model checking formal logic languages, that's how you would represent something like that. Simulated though, you're giving it the conditions. You could take real world test data, apply it to this model, and then in theory, get a accurate verification of your system. The problem with that is that a lot of these verification activities take a really long time to run. Simple systems run really quickly. Complicated systems, it can take hours to days to run a model. Just kind of depends on your application. All right, so testing. One more quote for you. So this is the canonical quote for testing. Testing is the process of executing a program with the intent of finding errors. So we've got some oddly colored text in here. What I want you to think about when we start, we're gonna more get into testing right now. But when you think of a test, you're looking for that green check mark, right? You're looking for a passing test. However, a good test is actually showing you the presence of a problem. And this is kind of a mental hurdle to get over, that when you're writing test cases, you want them to fail, right? Because if they fail, you're detecting the problems. Nobody's going to write a perfect program just sitting down and plunking it out. There's always going to be some problem that you didn't anticipate. And if you write a bunch of test cases and they all pass, you might get a false sense of security and think, hey, life is good. Let's ship it. No problems. Let's call that the Bethesda model. Um, but if you get an error, right, your test demonstrates there's a problem here, then you can fix it and augment your program and harden it. So, other thing too, testing only will tell you if errors exist. It will not tell you if a error exists and it's kind of hidden away. And this is kind of a hard thing to really also kind of consider. Basically, a test is going to show you that a problem exists. It's not going to show you that a problem does not exist. Basically, kind of the key takeaway here is that there basically is always going to be some error that exists. And your test is not going to tell you if something that you can't understand exists or not. It's only to tell you what you're testing. So, nice little quote here just to kind of keep in mind. If you have a test suite, again, collection of tests or test cases, think of it like an array of tests that you run. If they all pass, that doesn't mean that your program is perfect. Basically, your test suite maybe didn't exercise your program, meaning it didn't run through all the possible states. Maybe your test cases never even got anywhere near this bug. Um, Maybe the collection of input conditions never triggered this particular flaw. Um, what we're going to get into with some of these different testing methods is that a lot of really smart people out there have come up with these really interesting ways of doing testing. And even then, it's not guaranteed to find all the bugs. So let's talk about the psychology before we dip into the real aspects, and then we'll probably have to cut it a little bit short to talk about your next deliverable. Testing, if you remember from before, I've been harping on all of you about this over and over again. If you're the developer, you are not the tester. They should be two separate people, right? And there's a lot of psychology that goes into testing. And this can be something that is, again, hard to swallow, that you're not going to be the person writing your tests. The interesting thing with testing is that it tends to be very destructive, right? With testing, you want to break the program. Your entire goal is to demonstrate problems, demonstrate bugs that exist. You are writing test cases to literally break things. Okay? So do everything that you can to just destroy your system. Those of you working on games, I want to see clipping problems. I want to see seg faults. I want to see sprites not loading. I want to see inputs being mapped backwards, right? Every single possible case where your program can break down. Those of you doing a calculator application, I want to see what happens when you put a Unicode value in, or an ASCII value in, or an emoji in, right? What are all the possible things that something or someone could do to your program? You have to think of that and test for it, right? Um, you start going down that emoji code area. Does your smiley face do what you think it's doing? Basically, you want to break the program. That is your entire goal as a tester. And you, as the programmer, as the developer who has put their blood, sweat, and tears into developing this beautiful program, you don't want to destroy it. Whether, you can think that you can take the developer hat off and put on the tester hat and completely divorce yourself from your feelings, you're probably going to unintentionally overlook something. So, unless if you are the pinnacle of mental fortitude, I would really recommend you not be the tester. Now, the question is, though, this kind of contradicts what I told you last time, right? So we were doing test-driven development. You're writing your own test cases as you go. You're writing all of your unit tests, and you are doing that before you write a single line of code. How do you think that compares? So I think this is actually a good question to ponder. And if the stream is way behind, how does... Let's try this. Let's put a question into the chat for you all there. And you get some dancing crabs to think about. I think this is kind of an interesting, not really an ethical question, but it's kind of a paradox to think about, right? Because if I'm telling you to write unit tests for your own code, now I'm also telling you not to be the person testing your code. What's the takeaway here? Because this is not a professor screw up and saying the wrong thing. This is literally something you have to deal with. If you make the test first, it can drive robustness. Yeah, I like that. Definitely. Typically think of ways to make your code work instead of ways to make it not work. That's true. So with test-driven development, at least, we're writing our test cases first, right? So maybe let's think about where we are mentally. And this is like a little mental exercise. So you are sitting down to write the hello world of Godot programs or Unity or Pygame or whatever you're working on. Calculator-driven Java application. You have not written a single line of code yet. You write all of your unit tests first. I am mentally exhausted too. Um, Almost done. 2 more weeks. But if you haven't written a line of code yet and you're writing test cases, you are writing them to mirror your requirements, not your tests, right? Or not your code. So if you're doing test-driven development properly, at least, you're not really trying to break things. You're trying to, like you said, make it more robust, make it work correctly. You are still not doing the full testing cycle yourself. You're driving that, like you said, robust is a great word. I can't think of another one there. But you still are going to need a tester. You are still going to have to go through integration testing, system testing, acceptance testing, and these are all going to be done by people that are not you. And again, at these levels, the intent will be to break everything. And hopefully they do break stuff because then you can come back and figure out what went wrong and what you can do to augment your program. So definitely good points there. All right, so what we're going to do is we're going to end with the, feels like putting, hey, there we go, punctuation into a sentence before you write it. Well, if you do it that way, maybe that's the new writing thing for NaNoWrite month. Figure out your story structure and plot lines before you get the full story. That might not be a bad way to do it. But let's talk about some testing metrics here, and then we'll talk about the homework. So at its core, you're testing every possible state, right? The thing that you have to think about with testing are the actual timing economics of it. So the first one we're going to talk about is exhaustive testing. This is where you test every single possible combination. And the takeaway is that this is mathematically impossible to do. So this picture up here, I searched for exhaustive testing in Google, and this is from an exhaustive testing, I think, textbook. And then here, passed now for test case 5,690,000, so on and so forth. So we have, let me pop all these up. Black box and white box testing again. Like I said, get used to those words. We're going to be using them a lot. We can test the inputs and outputs. So that's your black box testing. We can test the paths of execution. We called it testing the algorithm inside the box before. Basically checking to make sure the behaviors are doing what you think they should be doing. Black box or white box. Exhaustively testing is, again, every single combination. This is impractical and impossible, generally considered impossible. So there are other testing techniques which we'll look at. Just to wrap it up here before we talk about homework, I wanted to give you an example of what exhaustive testing means. So here we have a very simple summation function. Takes two integers, returns the sum. Second easiest program in the world. First easiest would be hello world, right? Now, if we wanted to exhaustively test this, That means testing every combination of values, right? So what does that mean? Well, that's every combination of what A or B can take. And if you have a 32-bit system, that is 2 to the 32 times 2 to the 32, which gives you 10 to the power of 19 test cases that you have to run to make sure that this does exactly what you say it does every single time, right? That's what exhaustively testing means. And when you start thinking about testing functions, that means checking what are the values that each parameter can take. And if you're exhaustively testing an integer, you have to test every single possible integer that exists. So if one test takes a nanosecond, it'll take you 600 years to test the sum formula exhaustively. That's assuming you're doing it sequentially, not in parallel. Scale that up. 64-bit systems, 2 to the 64 times 2 to the 64. I haven't calculated it out, but it's even longer. So the key is that we're not going to exhaustively test everything. We are going to be smart about our tests, though. It depends. So does writing tests ever include software engineers writing mathematical proofs? That's if you get more into the verification side, honestly. That's where you have it's less a mathematical proof and more like a logic model in a way. So if you've ever gone down the formal logic or the formal automata, like you're writing state machines of your program, you are in this configuration based on inputs here, you transition over to this state, so on and so forth. Um, that's effectively a mathematical proof. And actually, I guess further, I have seen mathematical proofs that people have written for programs as well. Tend not to see it in industry as much, more academic or um, more in the, again, getting into the model level of things. But 1040, now at 1042, I said let's jump to the end. Let me, okay, up. Actually, let me pop out of here because I've got some animations. So here we go. This is like my favorite GIF in the world right now, except I don't like that it's flashing in the background. So I've mentioned last week that you're all gonna have to write tests for your project. Um, because that's kind of one of the other big things that is part of the software engineering process is writing test cases. And I've kind of left this intentionally vague because I wanted it to be part of your final deliverable. And I'm going to be looking for some unit tests, some integration tests, and some system tests. Now, these numbers are approximate. I'll give you the specific detail when I give you the test spec. Basically, this should not be something that freaks you out when you see this. Okay? And then your next assignment will be your last in scary Zelgo text. But when you look at this, again, a unit test is testing the smallest piece of functionality that you have, right? So does your function return the correct data type? Does a function return the correct range? When you press the left keyboard button, does your character move left on the screen? It doesn't have to be complicated. Your labs that we've done in class in the examples have all been JUnit based, right? Again, it doesn't have to be an automated test case. It can be something that you write out and prove that it works. So if those of you that are doing RPG Maker or Godot or Unity, you don't have to write a literal unit test. You can abstract it out. So it can be a mental unit test. Integration test, what is that? Well, you're putting two or more things together, right? So if you have one person working on the movement system, one person working on the camera system, does the camera follow the player when you hit the left button, for instance? Sorry. I swear, either I'm getting tinnitus or there's weird sounds happening. I feel like I'm going crazy on stream sometimes. So integration tests, putting stuff together. Again, doesn't have to be an automated thing. It can be just something that you write out. And then the system test. Does it work as a whole? Again, approximately 5 test cases that demonstrate everything working together. If you have any questions on this point, let me know, and I can help to clarify things. But kind of the key takeaway is that I'm going to be asking you to augment your requirements spec that we did at the midterm. Um, Now, it's not going to be a massive formal requirements spec, right? That would be hundreds of pages. I'm looking for kind of a lightweight version. Basically, what you'll be doing for your final deliverable is just revising a bit. And you're going to add a very lightweight test specification onto it. The test spec being these tests that I asked you to do. I will put that up very soon for you. It'll be up before your next homework is due, so that Friday. Basically, just to give you more time to think about it. But basically, what you're going to do is you're going to revise your requirements based on feedback I've given you, and have kind of a minimum threshold for how many you have. We'll have our test spec, any artifact stuff that you need to clean up. Like if I gave you feedback on your artifacts, I said, hey, this is crap, you need to fix it, or this is great, don't touch it, or you forgot to draw your boundary box, make sure you fix all of that. And it'll be basically one big happy package. Then I'm also going to be looking for traceability. So if you recall, your artifacts all had IDs, right? Or they should have. So you have functional requirement 1, non-functional requirement 5. You have use case IDs. You have your use case description had what it references, right? I'm going to be looking for that traceability between everything. Now, this will be lightweight, so it doesn't have to be fully comprehensive, but just be aware that's kind of what I'll be looking for this. Now, for timing, because we have 2 weeks until our final exam slot, you'll be doing your presentations on the Monday. I'm not going to ask for your deliverables until Friday of that week. So basically, you have all of final exam week to wrap it up and turn it in. And the reason why I'm doing this is I don't want to make it all due on Monday because I'm sure you all have other tests to study for. And I'd rather you take the time to put enough effort in, grammar-wise, revision-wise, to make sure everything looks good. Now, if you're done, turn it in. You'll get your grade sooner, and you'll be happy about that. But if you want to wait till Friday, that's fine too. Okay, questions on this little info dump on your final deliverables? Anything that you're not sure about? Let me get my huge face out of the way here so you can see the date. Here, is everybody good with this? So to summarize, we will continue on with V&V for the next handful of classes. Friday will be group work day. It'll be over Blackboard or Zoom, depending on what I'm in the mood for that day. I'll give you a link for that. Labs due Friday. Deliverables will be due 2 weeks from Friday. Absolutely. Yeah. So as soon as I put I just want to tweak the final deliverable requirement a little bit before I put it up for you all. I don't want to make it too overwhelming. As much as I would like to have it be overwhelming, I'm not going to do that. But yeah, I'll put an announcement up with a link and everything that you need. Yep. And I know that you're all working feverishly on finishing up your projects, so don't think that this is going to be something that will take away from all that effort. Basically, you're just constructing it and finalizing it according to the software engineering principles you've all hopefully learned this semester. And honestly, the test cases will not take you that long to come up with. Even if you had a Hello World application, you could come up with 5 unit tests pretty easily for it, or 10 unit tests. Alrighty, well, we will end for today. I'll see you all on Wednesday, and we will continue on with V&V. So, hope you all have a wonderful day, and I'll see you next time. Bye bye. Also, office hours start in 10 minutes.